Hello everyone, my name is Misty, and today we're going to be doing a more in-depth look, an in-depth guide on my operating system, how it works, and the bootloader specifically. This is part one of a longer series where we're going to go more in-depth and give a more tutorial aspect to the idea of an operating system and how you develop one. So my last video, the overview of everything, where I kind of just ran through everything, did a little showcase, it kind of blew up. We had a lot of comments saying people really wanted a tutorial, people were interested. So I thought, you know what, let's start it. So we're going to start from where it begins, the bootloader, okay? So here it is. We're going to go line by line through my bootloader, the actual first thing that runs when you power on the machine and boot Phobos. And I want to be clear, this is not a UEFI bootloader. This is a legacy BIOS MBR bootloader. 512 bytes, that's all you get. Everything you need to get from the CPU just woke up in 1982 mode. To a fully 64-bit long mode kernel. Has to fit in 512 bytes. Let's get into it. So, the first two lines, where we say bit 16 and org, that number. These two lines set the entire context. Bit 16 tells NASM, which is the compiler for assembly that I'm using. As you can see in my terminal, I have a pass command here. So NASM is the compiler, and we're basically telling NASM that we're assembling 16-bit real mode code because that's what the CPU starts in. Every x86 processor, no matter how modern, boots up pretending it's an 8086 from the 1978. That's just how it works. And this org line, this tells the assembler that the code will be loaded at memory address 0x7C100. The BIOS reads the first sector of the boot disk and drops it right there. This isn't a choice. This is a contract with the BIOS. Your bootloader lives at 0x7C100, period. That's it. It just lives there. That's just what's happened. So, these lines, move boot drive, and the AX stuff, all of these lines here. This is when the BIOS hands off to us. It puts the boot drive number in DL. Could be 0x80 for the first hard drive, 0x00 for floppy, whatever. We save that immediately because we're going to need it for later for disk reads, and we can't trust that DL won't get clobbered. Then we zero out DS and ES, exactly what the comment says here. Because yeah, we put 0 into AX, so we're basically just zeroing them out, getting them ready to do what we want with them. And then in real mode, memory addressing is segment : offset. So DS SI means DS times 16, because we're in 16-bit mode, plus SI. We set these to 0, so our offsets map can map directly to physical addresses. No surprises. You can't move directly into a segment register, so we go through AX. So we can't just do move DS 0x00. That's just not how it works. You have to put that into AX first, and then we can zero them out. This is only the first 6 lines. Okay, so we've got a long way to go. But if you're genuinely interested, hopefully this makes sense. Hopefully you find this helpful. So this is where we load the kernel. This is where we load the built version of kernel.c, which is in kernel, believe it or not. This is where we load kernel.assembly, and then we load kernel.c. But that's for the next video. In kernel.assembly, this is where it gets real. So we need to load the actual kernel from disk into memory, and we're using interruption 0x13 with the extended read function. So basically, the way everything works in assembly, you have interrupts. This is in 16-bit mode at least. So you have interrupts. So what you do, the CPU has registers, and you can move different numbers into the registers. This is really simplified. You can basically tell the CPU, like, yo, this number's 42, as we see here. This is blah, blah, blah. This is whatever. Now do the thing that you have on 13, please. And then it's going to look at the 42. It's going to look at whatever else we put in there. And it's going to be like, okay, 13, The arguments they're giving me is in these registers. Okay, cool. Now we'll do that. This interrupt 13, I believe, is the LBA based read. So it basically means like give me sector number n on the disk. So the way it works is you point SI at a disk address packet, a little struct that tells the BIOS how many sectors to read, where to put them, and which LBA to start from. Let me show you what packet looks like. So in DAP read, where's this? Down here, we have this code here. This is what a packet looks like, packet layout. This is what the disk looks like to the assembly. So this reads 127 sectors starting at LBA 1 and feeds them right after our bootloader at 0x7E100. That's about 64 kilobytes, if I'm not wrong. But we need more than that. A single read maxes out at 127 sectors on a lot of BIOSes. So we do a second read. This is where we have DAP read 2. So the second packet picks up at LBA 128, so right at the end of LBA 127 from this read, loads into segment 0x17C0 offset, offset 0x quad 0, segment 0x17C0 times 16 equals. Basically, we just have a load of hex, and we just kind of tell the BIOS like, yo, this is the hex stuff. Read this, give it to me, cheers, man. If the read fails, the carry flag gets set, and we can jump to disk error, which is up here. We see JC disk error, so that means jump. If that flag is set, we jump to disk error, which just halts the CPU. There's not much else you can do, you know what I mean? It's like if you start a computer, if you try and boot Windows without Windows installed, what's it supposed to do? Do you know what I mean? So now we have the VESA graphics set up. So this is pretty simple, actually. We're basically just doing what we did up here with the interrupts. We basically just say, yo, do this, blah, blah, blah. Just feed these numbers. These numbers, yeah, I won't lie to you. I don't really know what they're doing. I just saw it on osdevwiki.org or something. I'll put the link in the description. Just do a little bit of reading. Try and understand what you can. If you can't, don't be scared to ask ChatGPT. Just be like, yo, can you explain this in ways that make sense? Don't ask it to write code for you. It won't be able to. Just don't, okay? It will blow up your PC. Don't get it to write code. Just give it a concept. Say, how do I set up VESA mode in a bootloader, in assembly? And be like, I understand how to write it, but I don't understand what it does. Can you please explain it in X way or Y way? And it will give it to you in a way that it's easier to understand from an actual like understanding, like a deeper understanding point of view. So anyways, now the actual VESA mode, this basically sets up graphics. So there's two modes. We have, what's the other one? We have VESA for like controlling each pixel, and then we have, okay, I'm stupid, but there's another mode that basically means you can just print text and you don't have to worry about loading fonts or anything, but we are going to have to worry about pixels and everything. That's for another video. VESA mode, basically, yeah, we set up so we're in 1024 by 768 by 32 color depth. Now we're graphical. Cool. Page tables. This is here. So we need to move EDI, do this, do that. This is the part that makes people's eyes glaze over, but it's actually elegant once you see it. So x86-64 uses 4-level paging. You've got PML4, PDPT4, the page directory, and the page table. Each one is a 4096 byte table of entries that point to the next level down. First, we zero out 0x, this one. We zero out that. That's 3 pages, 12 kilobytes. Starting at address this, 0x1000. Clean slate. Basically, we just wipe this memory. Then we set up exactly 3 entries. So we have this one. This is PML4. And the abbreviations like the PML4, the PDBT, if you want to learn more, you got to look that up. You just kind of you just go with the flow. Like when you're writing a bootloader, you don't really have much control about what you're doing. You kind of just have to follow what the standard is for the industry. And there's not much room for difference because the CPUs are physically architectured in a way that expects code like this. So when someone says they wrote their own bootloader, it's nothing too crazy because it is just the same thing as any other bootloader. There's not much you can do about it. The actual operating system, you can have a little fun with it, but the bootloader is just copy paste pretty much every time in terms of what it actually does. Obviously, the actual code can be different depending on what you want to use it for, but yeah, so this is the page tables. Now we need to load ring 3. We just do this. And then we switch to long mode. So this is where we go from 16-bit real mode to long mode, which is 64-bit. If you've ever written any C, you'll know that long means 64-bit integer. So the switch to long mode, we move EAX into this. We move CR3. We move blah blah blah. And then this is just the ritual you need to do for long mode. Sorry, long mode is 32 bits if I'm not wrong. Actually, that's my fault. That's my fault. So we have to go from 16 to 32-bit to 64-bit. You have to go in order, otherwise it doesn't work. So this it's been a while since I wrote this. This is now we're in 32-bit after this. This is where we actually enable long mode. And then to enable paging and protected mode, this is 64-bit. My bad. Then we just do all of this. Pardon me. And then when we actually go to 64-bit, we do all of this code. We get the GDTs, we do all of this. And basically, we just kind of get it set up. Do you know what I mean? It's kind of hard to explain. We just kind of do it. And then, okay, let me go more in depth on the GDT. So, it's very important, by the way. We have 5 entries. So, we have a null descriptor. This must be all zeros. Fine. Kernel code. This is, I believe this. Yep. This is ring 0. So obviously kernel runs in ring 0. It's kind of why it's called like ring 0. It's like it's kernel mode. Anyways, the 32-bit flag here doesn't really matter in long mode for data segments, but we said it anyway just in case, you know. User data. This is this. We just this is in ring 3, by the way, because obviously if you know anything about even kind of how operating systems work, you have kernel in ring 0, user space is ring 3, and yeah, so basically we set up ring 3 here, and then user code, this stuff we set up in long mode. Same deal for when the kernel starts running user programs. Cool. And the boot signature, this is down here. So this is the last 2 lines. Times 510 minus dollar db0 pads the rest of the sector with zeros. So the way it works, the CPU loads from where it starts looking for the bootloader to byte 512. And basically, if we start writing other memory before 512, it will think that's the bootloader and it will start trying to load that. And then it'll break, right? So we got to pad it out. So we just got to fill the rest with null just to fill it out so we don't get random stuff booting in bootloader. So this is this. We actually pad to 510. Not 100% sure why, if I'm being honest. It's just the standard. So, and then DW this address. This is the magic boot signature. The BIOS checks for 0x55 at byte 510 and 0xAA at byte 511. If it's not there, the BIOS won't boot from this disk. x86 is little endian, so DW0xAA55 writes 55 first, then AA. Exactly what the BIOS expects. And yeah, that is the entire bootloader. 152 lines, 512 bytes. It loads the kernel, sets up graphics, builds page tables, switches the CPU from 16-bit real mode all the way to 64-bit long mode, and then jumps to the C kernel. Every modern OS has to do some version of this. The specifics change with UEFI, which is the more modern version, but the core journey is the same. You start in the Stone Age, which is, 16-bit. That's back in the 1970s. And then you build your way up to a modern environment before your kernel ever runs a single instruction. If you want to see the kernel side, what happens after the jump to the kernel, let me know. That's where it gets really fun. So thank you for watching. Hope you guys enjoyed. Any questions, feel free to comment. Any helpful resources to do with operating system development, I will link in the description. And thanks for watching. Like and subscribe. See you in the next one.